In this lesson, we will cover how the game data will be saved and how dynamic elements communicate with each other. The last scripts covered in the previous lesson are used to add stars to the background and keep them moving to convey the idea that we are traveling in space. The implementation is simple. We start by creating a scene for the star. It should have a sprite with the star. In this case, I will use this fragment of an explosion. To keep the star from being too big, we can change the scale to 0.5, for example. In the root node, we add the star movement script. Star movement is responsible for making the star move. The variables include speed, direction, and the maximum y position. This max y is used in the process to check if the star has reached the end of the screen and to position it at the beginning. It happens like this. The position is updated according to the speed and the duration of the frame. If the position reaches the maximum with a margin of 10 pixels to ensure it is completely out of the picture, the y value of position is inverted from positive to negative, making the star return to the top of the screen. This is a cyclical process, repeating indefinitely and giving the illusion that there are always new stars appearing at the top and others exiting at the bottom. In reality, they are always the same ones moving from bottom to top. The start star method is declared with two arguments. It expects a value for speed and another for the maximum y position. Upon receiving these values, the internal variables of the script are updated to the received speeds. This method is used to configure the star from the outside. But what configures the star? In the root node of level 1, we add a new node 2D and rename it to background stars. We add the background star script, and in the variables, we include the star, the total number of stars, and their speed. This script, in general, is for adding stars within the limits of the screen and assigning them a speed. This is done in the ready method. The first step is to check the size of the camera to calculate the minimum and the maximum positions, both on x and y axis. As soon as we have these values, we run the process of instantiating stars. But for this process to run the necessary number of times to instantiate all the stars, we use a for loop. The for loop repeats as long as a certain condition is true. Thus, for int I equals 0, I lower than star count I++ works as follows. Inside the parentheses, we have three parts: initialization, condition, and iteration. In initialization, we declare a variable with an initial value. In the condition, the logic that keeps the for loop running. In iteration, the operation that updates the loop variable after each execution of its body. The counter I starts at value 0, and as I is less than star count, which is 100, what is inside of the following brackets will happen. In the end, I++ increments the value of I by 1 unit. In the next loop, I, now with the value of 1, is still less than 100, and the loop occurs again. This will repeat 100 times because when I is no longer less than 100, because it has also reached 100, the loop is abandoned and the count continues in the line after the bracket that closes the for loop. And what happens inside the loop? The instantiation of stars. If the loop happens 100 times, 100 stars are instantiated. The instantiation process is similar to others already used in this series. The star is instantiated. The star's position is updated, but in this case not to the global position of the parent, but to an x and y coordinate chosen randomly within the limits of the screen, and added as a child of the background stars itself. After the star is placed in the location, the script star movement updates the star by changing the maximum y and speed values. In the next loop, another star will be instantiated using the same process. At the end of the for loop, we will have a field of stars moving in sync from top to bottom. However, in the previous demonstration, we had several stars moving at different speeds. The solution to this behavior is simple. In Godot, we duplicate or triple the background stars node And in each copy, we change the value of the speed and quantity. To better sell the illusion of depth, the slowest should have more stars and the fastest should have fewer. Now only the background color is missing. For this we had the color rectangle expanded to the size of the camera and with the correct color, in my case a very dark blue. To make the scoring work globally and to maintain the high score from one session to another, for example, we will need to create a save system. The save system will be responsible for saving and loading the necessary game values, creating and maintaining a file with this data, and allowing elements to have a centralized point of information. Create a script called GameData. This script must be accessible from any scene in the game. In Project Settings, under the Autoload tab, we open the GameData file and we add it to the list. This will load the file in the root as soon as the project starts. To access the script, make a reference in the ready of any other script, and we can easily modify the public variables, which is exactly where the game data will be saved. Copy the game data script shown here in full. The first 4 variables will serve the game, accounting for the score, the best score, the player's life, and how many enemies are still on the scene. The next 4 contains information related to saving the file with the data, such as the file name, file location, the password for encrypting and decrypting the file, and the last one with the password already translated into a format the encryptor needs. Config file is a Godot class already prepared for writing and reading files, and it is this class that we will use to keep the game data safe. Because the config file will need to know where the file is and the encryption key, the first thing we do is to prepare the path of the folder and create this key from our password. User : refers to the user's folder in the system and will be different on each computer. After this, in file path, we have the entire specific directory. The key will be encoded to hexadecimal and will look like this. Then we start the config file class and run the load data method to load the saved data. This happens at the beginning of the game whenever the player starts the executable. However, there will not always be a file. On the first use, the file does not exist, and this load data will give an error. To avoid this, in load data we start by checking if the file exists. If it does not exist, we create a new one with a variable's value at the moment, which will be 0. Save data saves by creating a new file every time, and that's why we simply save the file to create a new one. This will be built from scratch and saved in the folder by creating or replacing what is there. After that, the data in the file is read and placed in the variables. Here we only do it the iScore because the others will always be initialized during the game. The config file writes and reads data organized in 2 references: the section and the data name. The third argument serves in getValue to indicate a default value if the file does not have that reference, and in setValue to define the value to be saved. The saveData method does what the name suggests, saves the variable's data to the file. This starts by calling the updateConfigFile method, which creates a new file and updates all the variables to their respective fields, then saves the files to disk already encrypted. Encryption is important to safeguard the values and make them authentic. As an example, I will save the file without encryption to show you the difference. When running the game, GameData will create a file, this time not encrypted, and save the data inside as already described. But if we edit the file, the data is available, easy to read and change. While we are here, we can clearly see the section and the data organized in their respective identifications. Now, if the player saves these new numbers, they can return to the game and go to the internet to brag about having the best high score ever. To avoid this, we use encryption, which makes the data unreadable. The only way to access the data is to decrypt it using the key in the script. In summary, the save data script has several methods specific to each of the functions we expect from it. Load loads the data, save saves the data, and update updates the data before saving. These methods are used by the game elements to keep the game's progression recorded. To modify the data, we need to find a place where such an operation makes sense. We should avoid constantly reading and writing, so the process method is not the ideal location for this. Let's start with the player's health. The script that controls this is health. The problem is that we are using health in all elements that need to be removed. To clearly identify which health will control the player's life variable of game data, we will need a variable that allows this control. At the same time, it will be necessary to have access to game data. For this, we need a variable with a reference to game data, and in ready, search for the script which will be in the root. To change the value in game data, we simply call the variable and change the value of the variable there. At the end, we run the method that saves the value in the file. However, remember that this only needs to happen in the health that is in the player, so we need to verify this condition. We do this right at the end of the ready so that the level starts with the correct value, and this operation should be copied to the end of the increase health to keep the value within the limits, and right after the subtraction of decrease health to save the value before the player is removed. If we use a print, we can see the value in game data being changed with each impact. In Godot, in the player element, we have to mark the player's health so that it works as expected. Now we can work on the score, and this will also be in health. What we want to do is add points to the round score variable every time an alien is destroyed. To avoid adding points whenever any element is destroyed, since health is also in the lasers and in the player, we need to identify under in what conditions points are added. In this case, we declare an int variable with the value of points to add. This will have two purposes. First, it contains the value for the sum, but it can also be used to detect if it is a case to add. If the value is 0, nothing happens, but if it's higher, the score is added. Like in player life, we also need to order a save. This happens when health reaches 0, the moment the element is destroyed. Once again, with a print, we can check the operation. But to have a score, we'll have to go to the aliens and add a value. When running the game, we see that we are increasing the score, but not the I-score. For this, whenever the score is increased, we check if it has reached or surpassed the I-score, and if so, we save the same value in the I-score. As we can see, whenever we reach the I-score, it updates. And if we run the game a second time, we see that the save system is recording the information, as the old I-score value is still there. What we are missing now is to write this data in the game window and not in the output window. In the level 1 scene, we add a node called control. These green nodes are related to the interface. We expand the control area to the size of the camera and anchor it to the center. We add a panel to control anchored at the bottom left corner, and within the panel we add a label anchored to the left. The anchoring is based on the body of the previous node, allowing us to maintain rules for the location of the elements when formats change. In the label, we write score 99999 and adjust the font size to something more suitable for the size of the camera. We want to read it, but it doesn't need to be huge. With the text size defined, we adjust the dimensions of the label panel to be more coherent. These nodes have many settings and we should spend some time exploring and adapting the style to our game. For this demonstration, I will just improve the readability and highlight the elements. For the player's life, we copy the panel and anchor it to the bottom right corner. In the case of the right label, it is advised to align the text to the right as well. For these text boxes to write the values in game data, a script will be necessary. We create an inherited label script called writeScore and place it on the score label. In the script, we add a variable of the game data type, which we reference in ready. In the process method, we write in the text variable of this node, since the script is in the label, score with the value round score in game data. When running the game, we can verify that the value is updated in the interface, but there is a hidden problem. The value is being written in every frame, even when it's not necessary. Ideally, the value should only be written if it changes. To make this possible, we will transform process into update all labels and program a way to call these update all labels only when it's necessary. Godot has a communication system called signals, which we have previously used, and we might be tempted to use it in this case. However, what is really needed here is a classic observer pattern, which is a system where observers subscribe to an event and react to it when it's emitted, regardless of who sent it. The signals don't allow this because, with signals, those waiting for the signal must be directly connected to the element that emits the signal. In this case, as the signal emitter will be the aliens, who don't even exist at the start of the game, it would be impossible to connect the interface to non-existent elements. Therefore, what we need is an event system. The event system allows observers to connect to events instead of the event's source. This enables multiple elements to emit the same event and even for the event source not to be present from the beginning. Events also allow sending data with arguments and can be used to transmit data if necessary. Considering this, we will build an event system. The event system is composed of three elements: a global script that manages the events and their transmission, the subscription and unsubscription command, and the ordering of the event launch. Create a script named GameEvents based on node and add it to the autoload. Copy the entire body of the script shown now. Our first step involved defining a static variable, current, to reference the script itself. In the ready method, we assign the current instance of the script to this static variable. Thus, whenever we call current, we are effectively accessing the GameEvents script. This procedure is essential to create a singleton, that is, a global script accessible from any other game element. Then we implement an event manager mechanism. We create an event and a method to trigger this event. The event allows other scripts that have subscribed to it to perform their own actions when the event is triggered. Thus, whenever the update all labels method is called, it checks for subscriber, and if there are any, the event is triggered, making all subscribers receive the order to execute their methods. With this, the event manager is ready to function. If another event needs to be sent, just add a similar structure but with different names. Those sending the message or executing the event will only reference GameEvent and execute the intended method. In the health script, where we change the score and player's life, we add the following line of code after save data. Game event current update all labels. So, whenever the score or life is changed, the event is launched and the text boxes write the new value. To make this work, we are missing one step. We will have to write score the code to subscribe to the event. In write score, update all labels, trigger it right in ready, so the game starts with updated values. To make update all labels subscribe to an event, we just need to add it to the variable in the game events. Note that the plus equal sign is used to add the method to the event, and we are not summing values as we do in counts. Think of it as incrementing this method to the list of methods that the event executes. However, sometimes the subscribing elements disappear from the game, like the aliens when they are destroyed. If game events call a subscribed method that no longer exists, errors will occur, and to avoid this, we must remove the subscription when the script disappears. We had this method, which is executed when the element is removed, containing the reverse code with the minus equal sign. This removes this method from the event. In summary, game events contain variables to house the list of receivers and the methods that emitters use to trigger events. Those executing the event only need to call game events and the name of the method to execute. The receivers subscribe to an event, indicating which method will run, and unsubscribe when they are eliminated. Simple! When running the game, it appears we have the same behavior. The value changes when the alien is destroyed, but in reality, instead of writing the same value every frame, we are only updating when it's necessary. Having said that, and with this script functional, we duplicate the write score script and rename it to write player life, adding it to the label on the right. In the script, we change the class name to write player life as in the script name, and we modify the text to player life variable from game data with life in quotes. When running the game, we can see both panel updating the information. Copy the entire content of this lesson in full. Adjust the appearance of the interface to properly integrate the style and color of the game elements. Add a third panel for the boss health. Modify the necessary scripts so that the boss can write its life to game data and update the value on the interface.